In this video, I'll talk about intermolecular forces. They are the forces between molecules, atoms, or ions. But for simplicity, we just call them intermolecular forces. This type of forces originates from the interaction between charges. The electrostatic energy between two charges is 1 over 4 pi epsilon times Q1 times Q2 over R. This 1 over 4 pi epsilon is so-called Coulomb constant or electric constant. Q1 times Q2 is positive if these two charges have the same sign. Q1 times Q2 is negative if the two charges have opposite signs. And R is the distance between the two charges. When Q1 and Q2 have the same sign, this electrostatic energy is positive. We call that repulsion. When Q1 and Q2 have opposite signs, the electrostatic energy is negative. We call that attraction. Now let me ask you a question. Is there any attraction or repulsion between two helium atoms? Well, we know helium atoms are neutral. There's no net charge on any helium atom, but each helium atom consists of one positively charged nucleus and two negatively charged electrons. So if you have two helium atoms close to each other, let's say 10 angstroms away from each other, we can compute the repulsion between the two nuclei. And also there's repulsion between the electrons, of course, and attraction between the electrons and nuclei. So yes, there is attraction and repulsion between helium atoms. Overall, it's net attraction. This net attraction between helium atoms is really small, but also important because liquid helium does exist. If there's no attraction, we cannot make helium in the liquid state at all. So now let's look at the first type of intermolecular forces. It's called dispersion. Again, we'll talk about helium. Helium is an inert noble gas. Helium atoms are neutral, but again, there is attraction and repulsion between two helium atoms. Because, again, the nucleus of a helium atom has +2 charges. The two electrons in a helium atom each has a -1 charge. And then the electrons move really fast in the helium atom. How fast? Several million meters per second, or several thousand miles per second. So it's much faster than an airplane. So these two electrons, again, are surrounding the nucleus, and these two electrons can move almost in random motion, and at a certain moment, these two electrons may happen to appear on the same side of the nucleus like this. Alright? And then this creates a non-zero dipole moment on this atom. Look, you have the positive end here. The negative end is somewhere here between the two electrons. So we can actually draw a dipole moment from the negative center to the positive center. Alright, there's a dipole moment here. And then because of this dipole moment, it does affect the neighboring helium atoms. Because these two electrons are on the left hand side. And then let's look at this neighboring helium atom. It will respond in a way to have the nucleus closer to these two electrons. And then the two electrons a bit further away from this helium. So this is called instantaneous dipole here, and it induces a dipole here. So we call this instantaneous dipole, induced dipole interaction. And this induced dipole can induce another dipole in its neighboring atom as well. So again, we have the so-called instantaneous dipole moment because of the uneven distribution of the charges at one moment, and also it may induce a dipole in a neighboring helium atom. This is called induced dipole. And also it's possible for two helium atoms to have instantaneous dipole at the same time, and then they adjust their electron positions to attract each other. What's the magnitude of dispersion? There's a very wide range. It's from 0.05 to 20 kilojoule per mole. So for helium atom, it's 0.05 kilojoule per mole. But for some very large molecules, it can be as much as 20 kilojoule per mole. What's the reason? There are three reasons. When a molecule or atom has loosely bound electrons, so that means lower ionization energy, it's easier to remove an electron from this atom or molecule. And then we say its valence electrons can move more freely, and then this atom can create a greater instantaneous dipole. For example, the dispersion between neon atoms is greater than helium. Why? The ionization energy of neon is smaller than the ionization energy of helium. That means the electrons or the valence electrons of a neon atom is more loosely bound. They can change their positions more easily, and then therefore it's easier to have this so-called uneven distribution of the charges in neon. That will create an instantaneous dipole moment more easily. Therefore, the dispersion between neon atoms is greater than that between helium atoms. Similarly, the dispersion between argon atoms is greater than the dispersion between neon atoms. Reason number 2. When a molecule or atom contains more loosely bound electrons, the instantaneous dipole is going to be greater. For example, if we have C2H6 ethane compared to CH4 methane, the dispersion between ethane molecules is greater than the dispersion between methane molecules. Why? C2H6 simply has more loosely bound valence electrons than CH4. Similarly, the dispersion between this carbon-20, hydrogen-42, it's also a alkane molecule with more carbon and hydrogen atoms. So this molecule, assuming it's a long chain molecule with 20 carbon atoms bonded to each other, it's nearly 5 times as that between carbon-4, hydrogen-10. Why? Again, we have many more loosely bound electrons in this molecule than this smaller molecule. Number 3, the contact area between the molecules. So again, if we have two carbon-20, hydrogen-42 molecules aligned together, there's a much bigger contact area between these two molecules than between two carbon-4, hydrogen-10 molecules. So the shape and the size of the molecules matter. If you have carbon-20, hydrogen-42, it's bigger, and the contact area between such molecules is larger. What about the shape? Let's compare two molecules. One is called N-pentane, the other one is called neopentane. They both contain 5 carbon atoms and 12 hydrogen atoms. However, this so-called N-pentane has greater dispersion than neopentane. Why? Let's look at their different shapes. This one is N-pentane with a long carbon chain. This one is neopentane. So you have 4 carbon atoms all bonded with the center carbon atom. Now let's look at the contact area between two n-pentane. So this much. Let's look at the contact area between two neopentane molecules. It's much smaller. Therefore, we say there's a greater dispersion between two n-pentane molecules than that between two neopentane molecules. In all these examples, helium, neon, argon, hydrocarbons, they all have a zero dipole moment, but they do attract each other via dispersion. And again, this is why liquid helium exists. Without dispersion, there's no way to make liquid helium, liquid argon, liquid methane, because again, even methane, CH4, has a zero dipole moment. Although the electron negativity values of carbon and hydrogen are slightly different, the bond polarities cancel in CH4. Now I want to tell you this. The greater the dispersion, the more difficult to separate those molecules, and the higher the boiling point is. So now we can say the boiling point of helium is lower than that of neon, than that of argon. We know that. The boiling point of CH4 is lower than the boiling point of C2H6 ethane, which has a lower boiling point than an even larger C4H10 butane molecule. Now let's look at a second type of intermolecular forces, dipole-dipole interaction. I'm going to use HCl as an example, hydrogen chloride. They attract each other by having positively charged hydrogen arranged closer to negatively charged chlorine. Let's say if we have HCl molecules, and more likely you will have this hydrogen closer to the chlorine of another molecule. This chlorine is closer to the hydrogen, again, of a different HCl molecule. And this H and Cl are closer to each other, this HCl are closer to each other. Molecules arrange their orientations to increase the attraction. One specific example of dipole-dipole interaction is hydrogen bonding. Hydrogen bonding is one of the strongest dipole-dipole interactions. Hydrogen bonding occurs between a significantly positively charged hydrogen on one molecule and the lone pair electrons of a fluorine, oxygen, or nitrogen atom on another molecule. For example, it's possible to have hydrogen bonds between hydrogen fluoride molecules, between water molecules, between ammonia molecules, or you can have hydrogen bonding between one HF and one water, or between one water and one ammonia. The overall hydrogen bonding between water molecules is stronger than the other two, because on average, each water molecule can form 200 bonds, while each HF, hydrogen fluoride, or ammonia can only form one hydrogen bond per molecule on average. Let me show you the picture of the crystalline structure of water. Again, this is one water molecule. This is oxygen. We have two hydrogen molecules. We have two hydrogen atoms here. So, let's look at this hydrogen. This hydrogen can form one hydrogen bond with a neighboring water molecule. Same for this hydrogen. And this oxygen has two lone pair electrons, 1, 2. So in total, we have 4 hydrogen bonds being formed by this water molecule. However, if you say the number of hydrogen bonds is 4 per molecule, you just double counted every single hydrogen bond. Because if you look at this dashed line, it's a hydrogen bond. It's shared between this water molecule and this water molecule. To be fair, we count half of this hydrogen bond for this molecule and half for this molecule. So we have half, 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 and half here. So overall, each water molecule has 2 hydrogen bonds, or 4 shared hydrogen bonds. For hydrogen fluoride, because each hydrogen fluoride contains only 1 hydrogen atom, therefore, on average, there's only 1 hydrogen bond per molecule. NH3. We do have 3 hydrogen atoms available, but this nitrogen has only 1 lone pair. Therefore, there's only 1 hydrogen bond per ammonia molecule. So over here, you learned the concept of limiting reagent. In HF molecule, the limiting reagent is hydrogen regarding the formation of hydrogen bonds. Over here, the limiting reagent is the lone pair electrons, again regarding the formation of hydrogen bonds. So this is why water has stronger hydrogen bonding than hydrogen fluoride and ammonia. And water has a higher boiling point than hydrogen fluoride and ammonia. Now let's compare ammonia and hydrogen fluoride. The hydrogen bonding of HF is stronger than ammonia only because HF has a greater dipole. There's more positive charge on the hydrogen and a more negative charge on the fluorine. Again, the stronger the hydrogen bonding, the higher the boiling point. The boiling point of hydrogen fluoride is 20 degrees Celsius. The boiling point of water is 100 degrees Celsius. Ammonia, negative 33 degrees Celsius. Or you may convert those numbers to Kelvin. 293, 373, and 240 for HF, water, and ammonia, respectively. The reason I'm showing you these temperatures or boiling points of these molecules is because roughly the enthalpy of vaporization is proportional to the boiling point for all liquids. So given those boiling points in Kelvin, you can estimate the ratio between their enthalpy of vaporization, roughly. Now let's look at ethanol or alcohol. The formula is CH3, CH2OH. There's a hydroxyl functional group here. This hydrogen may form hydrogen bonding. This oxygen has lone pair electrons, but the hydrogen bonding between 2 ethanol molecules is weaker than the hydrogen bonding between 2 water molecules because, again, the rate limiting reagent here is the hydrogen atom. We have only 1 hydrogen atom here that can be used to form the hydrogen bonds. But if we compare ethanol and hydrogen fluoride, this ethanol has a higher boiling point. This indicates the hydrogen bonding between 2 ethanol molecules is greater than the hydrogen bonding between 2 hydrogen fluoride molecules. Why is that? Well, this is because if we just compare hydrogen bonding, this HF probably has a stronger hydrogen bonding than ethanol because of the greater dipole moment in this hydrogen fluoride. However, if you look at this molecule, it has a larger size and more loosely bond electrons from this carbon, from this hydrogen atoms, and this carbon, and this hydrogen atoms. So overall, the dispersion between 2 ethanol molecules is much, much greater than the dispersion between 2 hydrogen fluoride. So if we add up the dispersion and hydrogen bonding, this ethanol molecule wins regarding the attraction or intermolecular forces. And therefore, the boiling point of ethanol is higher than the boiling point of hydrogen fluoride. I think the boiling point of ethanol is roughly 78 degrees Celsius. HF 20 degrees Celsius. The third type is the so-called ion-dipole interaction. If we dissolve table salt in water, each sodium plus ion is surrounded by many water molecules. Same for this chlorine minus ion. And each water is a dipole, and there is attraction between sodium plus and its surrounding water molecules. There is also attraction between chlorine minus and the surrounding water molecules. And then ion-ion interaction. So if we just look at table salt in the solid state, sodium plus and chlorine minus attract each other strongly. If we dissolve them in water, there's still attraction between sodium plus and chlorine minus. However, every single sodium plus and chlorine minus is solvated by water. What does that mean? They are surrounded by water molecules, and they are more separated in water. So the attraction between sodium plus and chlorine minus in water is smaller than that in the solid state. Finally, there's dipole-induced dipole, ion-induced dipole interaction. This is simple. If you place a dipole or an ion near a helium atom or a molecule without a dipole, you can induce a non-zero dipole in helium or CH4. Finally, let's look at the magnitudes of the intermolecular forces. First, dispersion. It's between 0.05 to 20 kilojoule per mole. 0.05, we're talking about two noble gas atoms, in particular helium atoms. 20, you have to have a very large molecule interacting also with a very large molecule to have this much interaction, 20. So for example, if you have, let's say, carbon 20, hydrogen 42, with a very long carbon chain, if it interacts with another carbon 20, hydrogen 42, and then likely we'll have this much dispersion, 20 kilojoule per mole. Dipole-dipole. We're looking at this molecule. It's called a formaldehyde. This is carbon, oxygen, and then two hydrogen atoms. Oxygen is negatively charged, and over here we have a positively charged hydrogen atoms. This is the center of the positive charge here. So we have a dipole moment pointing from the negative end to the positive end. Same here, we have a dipole moment. Now the negative end of this molecule attracts the positive end of another molecule. And this dipole-dipole interaction has a magnitude between 3 and 20 kilojoule per mole. Hydrogen bonding is one of the strongest types of dipole-dipole interaction. For example, water, we have 3 water molecules here. Again, we have lone pair from the oxygen atom, and this is negatively charged, and then we have hydrogen atoms which are positively charged, and this hydrogen atom interact with the negatively charged lone pair electrons. This dashed line is a hydrogen bond, and we see another hydrogen bond here. The strength of hydrogen bonding is 10 to 40 kilojoule per mole. If we dissolve table salt in water, we have ion-dipole interaction. For example, this sodium plus in the middle, surrounded by, in this case, 6 water molecules. Well, it can be surrounded by between 6 and possibly 20 water molecules. And again, the sodium plus is positively charged. The lone pair electrons on the oxygen atom is negatively charged. There's very strong interaction between sodium plus and those oxygen atoms. The strength is between 30 to 100 kilojoule per mole. Now let's compare those numbers with the strength of a typical covalent bond. A typical covalent bond has a bond energy between 100 to 1000 kilojoules per mole. So this number is huge. So what kind of molecules have such a strong bond? For example, nitrogen molecule. There's a triple bond between the two nitrogen atoms. Or carbon monoxide. There's a triple bond between the carbon and the oxygen atoms. What about this end, the lower end, 100 kilojoules per mole? When two really large atoms form a covalent bond because the distance between the two nuclei is very large, the interaction is smaller, therefore we have a smaller bond strength. Finally, ion-ion interaction is salt. It's the largest, typically between 400 to 4000 kilojoules per mole.